Namaste. I, JVM, Narendra Kumar Sir, Assistant Professor, Department of Science and Technology, under Faculty of Education and Methodology at Jyoti Vidyapeeth Women's University. So, in today's session, we are going to discuss about elliptic curve cryptography. So, what is the elliptic curve cryptography and why this was needed? Why we are studying this? So, there are many reasons behind this. So, first of all, when we see there was an algorithm which was RSA. So why RSA failed? Because of its drawbacks. So let's discuss. So what is elliptic curves? So what are the curves? When we see in any graph, if there are some curves are drawn like this or something. So this is the standard uh, equation for that. That is y square is equal to x cube plus ax plus b, where a and b belongs to R. There is a number. So now talking about the characteristics of elliptic curve. So it has forms an abelian group and it is symmetric about the x-axis. Point of infinity acting as identity element. It's like is there any uh, point of infinity? Just like this curve is going somewhere here. So this is going to infinite. So this is this acts as the identity of elements, like it's parallel to the axis or just a straight line, or we can say in another manner. So these are some examples of elliptic curves, just like a is minus 2 and b is minus 1 here, b is 0, b is 1 and b is 2. So when we talk about this, so here this is, so when we see when we are increasing the b, that is the x-axis, so the curve goes like this. So this is going to the infinity. So when we see this is the axis, so these are the symmetric to x-axis. Every single curve is symmetric. See here, it's just a mirror image of the curve on x-axis. Now, when we talk about the finite fields, so we can say it's Galois field. So, what is the Galois field? Is there is a set of integers here that p raised to power n, and it goes like 0 to p raised to power n and minus 1, where p is prime number and n is a positive number. So we are taking a prime number here and a positive integer here, and this is a set of integers. This is completely set of integers. It's like Galois field or finite field, you can say. So it is denoted as f plus and x, where plus and x are the group operators. These are the group operators, and this is the function here. This is the finite field function here. So when we talk more about these, what is a group, what is the ring, and what is the field? So first of all, when we talk about the group, so here is the group, and then it is abelian group here, and including some more things here. So this is the ring, and then this is the commutative ring, then integral domain, and at the end, this is the field. So what are the things are included here? So first of all, there is a closure under addition and associativity of addition, adaptive identity, and additive inverse. These four things are included in a group. Then when we talk about the abelian group, so what is the abelian group? This is commutatively of addition is also added to this. So this is completely an abelian group. Now when we talk about the ring, so these things are included, but some additional things are also here. So first one is the closure under multiplication. Second one is the associativity of multiplication. Third one is the distributive laws. So when we include all these, so these things come under the ring. What about the commutative ring? So we add one more thing to it, that is commutatively of multiplication here. So this is completely a commutative ring here. Now, when we talk about the integral domain, so multiplicative identity and no zero devices, these are also included here. Just like we are dividing by zero, so this make nonsense. This leads to infinite if the value is n here. This might be a positive or negative integer. So if it's a negative, so it's minus infinite, and if it's positive, then it's just infinite. So this does not make any sense here. At the end, multiplicative inverses, just like we are multiplying and then we are inversing that. So these also are included. So all these things come under the field. Now, why elliptic curve cryptography? Why we use the elliptic curve cryptography? Because of its shorter key length and the lesser computational complexity. What is the computational complexity? When we calculate a key, so there are some mathematical operations there. So if we are calculating such function, or we are deriving such function, so it may take longer time than the usual. But here a lesser complexity is there. Now, third thing is there is a low power requirement. Just because lesser complexity, shorter key length, it will require the low power, and it is more secure. Why it is more secure? We will talk about this in the later slides. Now, the comparing the key sizes of equivalent security. So first one is the symmetric encryption. Now, all the key sizes are given in the bits. Second one is given for RSA and Diffie-Hellman modules, size in bits here. Then the ECC key size. So when we use the symmetric key, the 56 bits are equivalent to 512, and in ECC it's just 112 bits. So by comparing all these, we can say these are some lesser key sizes here. Lesser key sizes are here by comparing RSA. So in RSA, when we are using 15,360, then it just can do it in 512. Just because in symmetric cryptography, the security is compromised or security is less. So we can see here some uh, more key sizes. Now, what is the elliptic curve cryptography? So it is it implementing group operations. Main operations are point addition and point multiplication. So adding 2 points lie on the elliptic curve result in the third point on curve. Just like we are drawing a curve like this. So we are just adding 2 points. There's nothing else. Like here to here, then here to here. Just small points are added to here. The P is known as the point of the curve. It's this point and part of the domain parameters, and it's multiplied by scalar k. It is q kp. Q is equal to kp. This is the operation adding of p at k times k multiplied by p. This is q is equal to k is multiplied by p. Just like here, kp means k times p. Now q is the resulting public key. This is the resulting public key, and k is the private key. This is the private key in the public private key pair. So this is the private key. We can say this is the private key kr, and this is the public key ku. Now, when we see 2 points are added here, p and q are added here, and to obtain the p and q, which reflections are along the x-axis. So we are adding this, and we are taking the reflection of this about the x-axis here. So a tangent at P. Now we can see P here, and we are just adding here, here. So what is the thing? Adding P and P gives 3P. So this is the P, and 2P gives 3P here. Similarly, such operations can be performed as many times as desired to obtain this. So we are adding these. It's like this will be added like this, like this. Now triangle will be built just like this. Now, what is elliptic curve cryptography again? So this is a discrete log problem. The security of ECC is due to intractability or difficulty of solving the inverse operation of finding K given Q and P. So this is termed as discrete log problem. Methods to solve include brute force and Pollard's RH attack, both of which are computationally expensive and unfeasible. Just like a symmetry key, in the symmetry key, the key was cracked so early by using the brute force. So within the minute or within seconds there. Now the version applicable, this version is applicable in ECC is called the elliptic curve discrete log problem here. ECC, EC DLP, discrete log problem here. The exponential running time is here. So when we see about the ECC in Windows DRM version 2.0, so the finite field is chosen this like this P, and we find the Gx and Gy here. What is the y square is equal to x cube, and we are just adding these values here. So Gx and Gy constitute the agreed upon the base point P, and the numbers in the above equation are values of the parameters of A and B. So these are the values of A and B here only. So when we see about the schemes which are related to the elliptic curve schemes, so it is related to elliptic curve cryptography. So first one is the ECDSA, which is elliptic curve digital signature algorithm. Second one is elliptic curve pinstone one stone signature, ECPVS. Third one is elliptic curve Diffie-Hellman, ECDH. Now, when we talk about the first one, what is this? So elliptic curve digital signature algorithm, ECDSA. So what is the thing is here? When we talk about the Canadian postage stamp, which use the ECDSA. So there is a security code, there is a creation time, postage amount, mailing date, creation date, counter rating, vendor identification, ad plate. Here, digital two-dimensional barcode. This is two dimensions, like this is their data, like this middle serial number. So these are all the things which are available on this small postage stamp here. Now, signature generation, how we generate the signature here. So once we have the domain parameters and have decided on keys to be used, the signature is generated by the steps like first we take a random number and then we compute kz, where it's equal to x1 and y1, where x1 is converted to its corresponding integer x1. Next, we take the r, that is equal to x1 mod n. Then we compute k inverse mod q, and then we take the value e, which is the hash of m, where m is the message to be signed. So we are taking the hash on that message, which is the value of e. At the end, the signature is the signature is the random values inverse, and then the hash value of m, and then we are taking dr, d and r multiplied by each other, and then mod n. So here d is the private key of the sender, r is the value we have taken earlier, just like this is the x1 here. So this is the final formula. Now we have the signature as r and s. So we have the signature is like x1 s, and in the s, this these things will be connected. How we verify the signature? This is the vice versa steps will be taken here. At the receiver end, whether the I and S, it will see the whether R and S belong to the interval this, For the signature to be valid, then they compute the E, which is hash of M, and then compare it. Then compute W, which is the S inverse model, compute U1, then compute X1, Y1, that is this, and uh, the signature is valid for R is equal to X1 mod and invalid otherwise. So this is the process here. Now we talk about the segment. So elliptic curve pin store, one stone signature. So this scheme uses the elliptic curves. This is more efficient than RSA, and and the overheads are extremely low here. When we talk about this, we choose a random number, we calculate the point R on the curve, then we use R and a symmetric encryption algorithm to get the E. Then we calculate a variable D, so this is like a hash of E or IA or V here. So I is the identity of mailer terminal here. So when we take these things here. Now calculate the other part of the signature as follows. Just like we are finding S, this is the A multiplied by D plus K and mod N. So this is the private key of the sender. And the signature pair is SE here. So this is transmitted together with the portion V of the plain text. How we verify this? We retrieve the QA, which is the mailer's A's public key, and then we calculate the D using the same scheme, and then we compute U, and then when we compute the recover here, and run an redundancy test on C. So if this test fails, so we discard the message, or otherwise the plain text is recovered here. So we have the S is equal to A multiplied D plus K. So multiply the base point Z to obtain the SZ is equal to ADZ plus KZ, which is DQA plus R. So therefore, so R is equal to SZ minus DQA, which is U. So comparing the decrypt versions M and M dash obtained using U and R, the ascertain validity of the signature. Now we come to the Diffie-Hellman. So elliptic curve variant of the key exchange Diffie-Hellman protocol. So it decide to domain parameters and come up with a public-private key pair. So we already know that there is a public and private key pair. Now, to obtain the private key, the attacker needs to solve the discrete log problem. So we have talked about that earlier. So how the keys exchange take place is like there are two members, Alice and Bob, publicly agree on the elliptic curve E over a large finite field F and point P on that curve. We are taking three things here: elliptic curve E, field F, and point P. Now, each privately chooses a large random integer denoted by A and B. So they choose A and B here. Now, using the elliptic curve point addition, Alice computes AP on the E and sends it to the Bob. So AP is calculated and sent to the Bob. Bob computes BP, and on E and sends it to the Alice. Okay, so the random numbers are taken by them are different, might be the same, some in some rare cases. So both Alice and Bob can now compute the point ABP Alice by multiplying the received value of BP by a secret number A and Bob by vice versa. Just like if the B will apply the P here and A will apply the A here. So this is the final value A BP here. So Alice and Bob agree that the x coordinate of this point will their shared secret value here. Now, what are the pros and cons of the elliptic curve cryptography? So first one is in the pros. The first one is the shorter key length. So same level of the security as RSA achieved as short key length. It's better security, like secure because of the ECDLP. Now, higher security per key bit than RSA, and the higher performance is there. What are the cons? So it is relatively newer field. So idea prevails that all the aspects of the topic may not have been explored yet. possibly unknown vulnerabilities might be there. So this don't have the widespread uses. No, this is not the perfect algorithm for cryptography. Why that? Because the attacks still exist that can solve ECC 112 bit key length has been publicly broken already. So this is not the perfect here. Now, well-known attacks are the Pollard's RHO attack. Complexity is the order of root n, Falling's attack, Baby's step, Giant step, etc. So these are the things about the elliptic cover cryptography, where we discuss about many things. So this is all about the session. Thank you.